Hello guys, good evening everybody. My name is Bafata. As you know, today we are going to see our second class in control system. In the previous class we have seen that introduction about the controls system. So today we are going to see modeling of the mechanical system. This is one of the portion in this control system. So modeling of the mechanical system is our today's title. When we start to see this portion, there are two types of modeling of the mechanical system. These are the translational mechanical system and rotational mechanical system. So when we see one by one, when we see the mechanical translational system, here the force is input and the displacement is output. Okay, where when we see the rotational the mechanical system, the torque is input and the angular displacement is output. So this is the short introduction of the types of the mechanical system. When we see deeply into the translational mechanical system, like the electrical networks, mechanical system have three passive linear components. These are mass, spring, and vicious damper or dissipate switch energy. So both mass and spring are one of the linear components of the translational mechanical system, where they store they are called the energy storage elements, whereas the viscous damper is one of the mechanical translation system, but it dissipates energy, not store energy. Okay, this is the difference among these three linear components of the transition mechanical system. When we see mass represents weight of the mechanical system, whereas spring represents the elasticity of the mechanical system. Okay, so mass represents the weight of the mechanical system, whereas the elasticity represents the spring, or the spring represents the elasticity of the mechanical system. Okay, and the viscous damper represents the friction in the mechanical system. Okay, this is very important things in this translation mechanical system. When we see the basic elements of the translation mechanical system, the force balance equation, this is the first and the important equation in the transition mechanical system. So as we know, mass represents an element which resists the motion due to inertia. This is, as we know, this law is the Newton's second law. The Newton's second law says that which deals with the inertia, right? Yeah, inertia. It represents an element which resists the motion due to inertia. Yeah, according to the Newton's second law of motion, the inertia force is equal to the mass time acceleration, or the product of mass and the acceleration which produces inertia. That is the Newton's second law principle. So when we see diagrammatically, this force balance equation will be like this. So this is mass. This is an object which has mass, and this is x of t means displacement, and this f of t means the force, which is applied force. So when we see it's the mathematical formula, f of t is equal to t means nothing but the time, because this force is the function of time. So f of t is equal to mass time acceleration. F of t is nothing but the applied force which is applied to the mass on the mass. Okay, so f of t is equal to mass time acceleration. So so nothing but here, nothing but acceleration is nothing but d square into x of t over dt square is acceleration. This is mass. So we can say that this part is the expression after the equal sign is known as the opposing force developed by mass, and this is the left part expression. F of t is the applied force. So when we apply the Laplace transformation of the above equation, the Laplace transform of the above equation will be f of s is equal to ms square into x of s. Okay, this is the Laplace transform equation for the above equation, because this is the first equation is the time domain, the time domain, and the second one is in the frequency domain. Laplace transform is nothing but changing the equation from time domain to the frequency domain. So this is done by after this process we are going to go another step. So here we are using the Allenberg's principle, which is similar to the Kirchhoff's laws in electrical networks. Also, this principle is a modified version of the Newton's second law of motion. The D'Alembert's principle states that what states is the D'Alembert's law. We are going to see the D'Alembert's law. So in the D'Alembert's law, we can see that the principle states that the principle states that for any body, the algebraic sum of the externally applied forces and the force opposing the motion in any given direction is zero. So this is nothing but the Allenberg's principle. So after this, what we are doing is here the Visquez damper. In the Visquez damper equation, the first one is based on what we are doing, the function based on the mass, but here we are doing based on the Visquez damper. So this is nothing but the Visquez damper. So this is the displacement and this is the applied force, or we can say the Visquez damper as dashpot. We can say or B, we can represent in B or D or FV. So it's all are same is dashpot. So FV is Visquez friction. Yeah, we can represent the Visquez friction coefficient f of t is equal to fv dx of t over dt. This is in first derivation because it is viscous friction or viscous damper. If it is mass, it should be in second derivation. That means we can use d square x of t over dt square, but here we are using the first derivation. So f of t is equal to fv dx of t. Fv is nothing but the viscous friction coefficient. So here the expression at the right side is applied force, and the expression after the sign equal sign is opposing force developed by viscous damper. So now we are going to change the above equation, the time domain equation, into the frequency domain equation. So that means we are changing to Laplace transform. So the Laplace transform of f of t is equal to fv dx of t over dt is equal to f of s is equal to fv s of x of s. This is the Laplace transform. This is, as you know, this is the diagram for this equation. These both are same, but we are using here in the time domain. Yeah, here this diagram is for time domain, and this diagram is for frequency domain. So it seems like this for according to the viscous damper. When we see the applied force according to the K or the spring constant, so this is the diagram for that in a time domain. This is the spring. This is the spring. This is f of t. This is x of this displacement, and this is the force, the applied force. So we can say that the equation for this translational mechanical system based on the spring constant, f of t is equal to kx of t. K is nothing but the spring constant. So here we can say that this f of t, that means the expression at the right side is known as the applied force, and this is opposing force developed by a spring constant. That means nothing but the expression after the equal sign. So we are going to change into the frequency domain. That means we are changing this above f of t kx of t equation into the Laplace transform. So we can get f of s. S is nothing but for Laplace transform. S should be the capital S. F of S is equal to F also should be capital. This S also should be capital. So for Laplace transform representation, so kx of S, F of capital S, capital F of capital S is equal to k capital X capital of S. This is the Laplace transform. So the other thing is, this is the diagram for force displacements for a linear spring. The force, force is the displacement. So this is displacement. The horizontal is displacement, and the vertical is the force, because displacement should be in the x diagram, that means x-axis, and the force should be in the y-axis. So the diagram seems like this, or diagram look like this, because it's a linear. It's a linear. Okay. So if it's linear, the line also could be a straight line or linear relationship. Okay. So this is the spring. This is the spring. This is displacement according to x1 of t and x. Now what we are going to see is what will be if two displacements are connected or associated with two displacements. And in the above, we have seen that the equation by using only one displacement, but now we are going to see when the two displacements are attached or connected. So there are two displacements here, x1 of t and x2 of t. Here also is according to spring, this is according to Bezier damper. Here also two displacement we have. So what we are going to see is we are comparing both two. So with respect to first node, that means this x1 of t, we can say that f of t is nothing but the applied force is equal to a spring time x1 of t minus x2 of t. This is according to the first node. For what? For spring. According to the first node for Bezier damper, so f of t is nothing but the applied force is equal to fv is nothing but the Bezier damper coefficient into x1 of t minus x2 of t. This is with respect to the first node. It is the Bezier with the Bezier damper. We are going to see the f of t or the applied force. So when we see according to second node, so according to second node, so for a spring constant, f of t is equal to k x2 of t minus x1 of t. This is for a spring constant with respect to the second node. The second node is nothing but x2 of t. For what about for Bezier damper with respect to the second node, f of t is equal to fv into x2 of t minus x1 of t. Okay, so now we are going to see the example on this. The example says that find the transfer function for this the given example, or that means this one. So this is the example given here. The spring is there, dashboard is there. We have only one displacement, and we have force and applied force, and this is also mass. Okay, so first our first equation is what nothing but our first equation or our first process or step for this sorry. So we are going to solve this the given example. So our first step is drawing the free body diagram for this above diagram. We are changing into the free body diagram. So when we draw the free body diagram, this will be like this, because here the spring we have. So one force is here, and here we have dash spot, because it dash spot. This is another force we have. Here we have the mass also. Mass. There is mass. There should be another force we should have. So here another force is there. This applied force. So now we are changing into this equations into the Laplace equation, or we are changing all this, we are changing to the Laplace equation. Okay, we have changed this. Okay, obviously this S is S, and here is in the time domain, this is in the frequency domain. So when we write in equation form, we can write like this. So f of t is equal to m times d square x of t over dt square plus fv dx of t over dt plus k into x of t. This is nothing but sum of opposing force is equal to applied force. So after this process, what we are doing to do is after this process, what we are doing is taking Laplace transform for the above equation. So when we take the Laplace transform for the above equation, we can get ms square x of s plus fb x of s plus kx of s is equal to f of s. F of s is nothing but the Laplace transform form of f of t. Okay, so we can get that f of s is equal to we are taking the common x of s, and x of s into ms square plus fbs plus k. This is when we take the common x of s as a common, so we are getting this equation. So now we are going to get the transfer function. Transfer function is nothing but the transfer function is nothing but the ratio of the ratio of the ratio of the output to input. Yeah, the ratio of the output to input is nothing but the transfer function. That means g of s is equal to x of s over f of s. G of s is nothing but the transfer function, and x of s is equal to the displacement, which is the output, and f of s is nothing but the force, the applied force, which is nothing but the output. So this is equal to, we can get 1 over ms square plus fbs plus k. This is the final transfer function form of the given equation. So here the second example is given as you have seen in this diagram. This is the equation given. Here we have three springs we have, two masses we have, and two dash spots we have, and three or around two or three displacements we have. So here when we start to solve this equation, each mass element gives one linearly independent displacement. Here each mass element gives one linearly independent displacement, or mass element mass element is the point of the displacement. Okay, so at each independent point of motion, one differential equation is obtained. Okay, obtained, that means number of differential equations is equal to number of mass elements. So we have to know this carefully here. So here the differential equations are two mass elements. Okay, so here we have I think we have two displacement no, we have two differential equations, I think. So f of t is equal to m1 d square x1 over dt square plus fv1 dx1 over dt plus fv3 d into x1 minus x2 over dt plus k1 x1 plus k2 into x1 minus x2. How we got this is the first equation. How we are getting is this is with respect to first node, which is nothing but x1 of t, and for m1, that is mass 1. For mass 2, we have no applied force, no any applied force. So if there is no any applied force, we can say that f of t is equal to 0. So 0 is equal to m2 d square x2 into dt square plus fv2 dx square over dt plus fv3 fv3 d into x2 minus x1 over dt plus x3 k3 x2 plus k2 into x2 minus x1. This is the second equation. So we can say that for m1 f of s is equal to, that means we are changing the above the first equation into frequency domain. That means we are changing into the Laplace transform form. So f of ft will be f of s is equal to m1 s square plus fv1 plus fv3 into s. That means we are taking the common s plus x1 plus x2 into x1 into s. This is here also we are taking x1 into s into as a common minus fv3 s plus x k2 into x2 of s. This here also we are taking the x2 of s as common. For this is for second equation, and for first equation. When we see for second equation, as we know there is no any applied force for second equation, so we can say that 0 is equal to minus into fv3s plus k2 into x1 of s plus m2s square plus fv2 plus fv3 into s plus k2 plus k3 into x2 of s. This is nothing but the the Laplace transform form of the second equation, which has no any applied force. That means the applied force is equal to here 0. So the transfer functions for x2 of s, f of s is x2 of s over f of s is equal to g of s. This is nothing but the transfer function, which is equal to fv3 is plus k2 over delta. So delta is nothing but the determinant value of the matrix which we got from the above equation, above two equation. So we can form to solve these two equation. We are using the determinant value. So in the determinant value, what we are using is the coefficients as the matrix. To form the matrix, we are using the coefficients here, the coefficients of this f of s, and that means the coefficients of x2 of s. So we are using as the determinant. That means as a coefficient we are using, and like this we form the matrix. Then we solve this matrix by using the determinant formula or the determinant method. Matrix determinant method we are solving, and finally we will get the final answer for. That means the transfer function will be find x2 of s over f of s is equal to g of s. That means we will use we will divide this fv3s plus k2 over that the determinant value of this. The delta means nothing but the determinant value of this matrix. So this is, I think this is enough for today's class. If you have any questions, suggestion, you can ask me in the chat or in the comment place. You can ask me, and I think it's very enough for today. Thank you for following my classes.